Okay, so good afternoon and welcome to all of you. Those people coming in, there are snacks at the back, and those of you online are just out of luck in the snack department. So my name's Sally Aitken. I'm the Associate Dean Research in the Faculty of Forestry, and it is my great pleasure to welcome you here today and to introduce Dr. Qingshi Tu, who will be giving today's research seminar. Dr. Tu joined our Department of Wood Science in 2020. Of course, that was right at the start of the pandemic. Yeah. So he just mentioned he hasn't given a lecture in this room since he gave his job talk. Yeah. But it was a very good job talk, so it will probably be a very good seminar today.
Yeah, I hope so.
And part of the point of these seminars is so we can see each other once again and hear from all the some of the great new people who have joined us. So Qingshi's an assistant professor of industrial ecology, and before he came to UBC, he was a postdoctoral associate at the Center for Industrial Ecology at Yale, and he was conducting research on the relationship between resource efficiency and climate change. And this is such an important area that he's going to talk to us about today, is really on how we have the sustainable development of the bioeconomy and bioproducts. So he's worked in areas of bioenergy, biofuels, and bioproducts, and he's really focused on developing open source databases and models for evaluating sustainability of new technologies and engaging different stakeholders in these processes. So with our great interest in bioproducts at UBC and with the Bioproducts Institute, and with other initiatives, we're really happy to have Qingshi here to work on these issues.
Thank you, Sally.
Thank you very much, and we'll be taking questions at the end via the chat or in the room.
Thanks. So my voice is still okay? Online? Okay. Yeah. All right. Thank you everyone for coming to my talk. It's really nice to see many familiar faces in the flesh. And so I think in the next 45 minutes or so, we will together explore some of the key areas in bioeconomy and how we can use industrial ecology methods to help those aspects to be more sustainable. So, all right. So let's take a moment and think about when you first think about the term sustainable bioeconomy. What is the kind of the first thing coming to your mind? Right? For a lot of us, I think we'll immediately think about like biofuel, bioenergy, bioproducts, and I think the intuition is quite straightforward, right? So we want to use these novel technologies to replace fossil-based benchmarks so that we can actually mitigate climate change impacts and help to conserve our limited resource, and in some case to help to like secure our energy supply. And this list actually goes on and on. But this is a very important, like the core part of the bioeconomy is the technology, but it's not a full picture, right? So for the bioeconomy to be truly sustainable, we need to have, for example, the societal support. If you think about all these new emerging technologies, bio-based technologies, without a societal support, it won't take up, right? So then it won't reach the potential it's supposed to be. So societal support is very important. And then at the same time, the sustainable biotechnologies should be able to give back to the society, for example, to help to reduce the inequity in affordable energy, and also help to create job in the economy, right? So, and of course, we want to be at least not worse off in terms of resource conservation and environmental protection, right? So if we look at this whole picture, actually, it's again, not just about technology, but we really need to think in a systematic way to consider the social, economic, and the environmental aspects. So this is really like a giant question, the topic area, right? So if we zoom in a little bit into a particular topic that many of us are familiar with, I think many of us are interested in what's called integrated biorefinery concept, right? Where we use a series of technologies, for example, biological, chemicals, to produce a wide range of products. That's the goal, right? Fuel, energy, chemicals, materials, so that we can replace the fossil-based benchmark. But in order for this practice to be sustainable, I guess many of us, especially I think the colleagues in FRM, will actually immediately think about supply of the woody biomass, right? We actually have sustainably managed forest. Like in Canada, it's largely the case, but not like always the case in different countries, right? So we may actually be like constrained by the supply of those sustainable woody biomass to begin with. So that's the upstream consideration. Then if you think of downstream, the sustainability implication can be more complex, right? How the products are distributed, how people are using the products, and how people actually get rid of the end of life products are all going to come into play and eventually going to impact what we call the planetary boundary. So this like a radar figure basically shows like the multiple planetary boundaries. And I think as you can probably think of, like climate change is one of them, biodiversity is another one, water quality, right? So all these important aspects will be affected by our development of a bioeconomy itself. So the question again is how can we prevent these negative consequences from happening, right? So one way of doing this is we need to be able to measure or at least estimate potential impact. That's where actually industry ecology methods come into play, right? And I guess before this seminar, probably some of you have never heard of the term industry ecology, right? So let's take a step back and just look at a term that probably more familiar to most of us, which is the ecology, the natural ecological system, right? So in this system, as you can see, we have different entities, where we have human, animals, plants, and then I would like to direct your attention to three very fundamental type of flows that actually support this type of natural ecological system. The first one is what I would call the energy flow, right? So in this case, we have direct energy from the sun. And then the second type of flow is, in this case, is the food, right? So the food for human, food for animals. But if you think more broadly, food is a type of material flow, right? So we have energy flow, material flow, and then next we will have waste generation. So that's the waste flow. So these three type of fundamental flows actually form kind of the foundation of a natural ecological system. And the ingenious way of our natural ecological system is that in many cases, the use of these flows are optimized. So we will minimize the generation of waste that actually becomes like non-recyclable. So that's kind of minimized. So then if you think about industry ecology, right? So we still have the ecology term here, and the study area of ecology in this case is the same. We want to look at the three major type of flows and how that's actually going to impact our environment and resource. But the difference is that we are focusing more on the technology, like human activity, product systems, supply chains. So hopefully this analogy gives you a bit better like understanding about like what industry ecology is. And then as a discipline, right, industry ecology actually involves a lot of methods that you can use, for example, to understand the sustainability of a particular industrial system. And I guess, again, many of you probably heard of the term life cycle assessment, LCA, right? So, and in many cases, people think industry ecology is LCA. But as you can see here, it's not the case. LCA is one of the major methods of industry ecology. And we use LCA to try to understand, let's say, the environmental impact of a particular product from its resource extraction all the way to its end of life treatment. So applying LCA is usually at, let's say, in terms of scale, it's product system level. And then, of course, recently people also want to use this more like life cycle, like a philosophy to look at a social impact. So that's why you will probably also heard of a term called a social life cycle assessment, right? Then the second method I will briefly talk about is called environmental input and output analysis. So the very fundamental difference between LCA and in this IO analysis is that the scale of the analysis. So again, LCA is more on the single product system level. And if you are familiar with macroeconomics, input and output analysis is more like an economic analysis. You look at how a change of a particular industrial sector, economic sector, is gonna, the demand of that sector is gonna change the output of the other industry sectors. So we're talking about really at a macroeconomic level, how the change, let's say, in the forestry sector is gonna actually affect all the other sectors' output, right? So, and then you can couple that with the environmental analysis. So that's where the environmental input output analysis actually comes into play. But again, I hope you get a sense, get a feeling, right? So LCA is more like a single product, like a more specific high resolution type of modeling. Then environmental IO analysis is more like a higher, like larger scale, but like a lower resolution type of analysis. They're both important. And the third one is also at like a more like aggregate level or a higher level analysis called material flow analysis. So basically it keeps track of the stock and flow of a particular material, let's say wood, through a particular system, let's say a construction sector, right? Let's assume in 2050, there will be certain like area demand for people to live in the city of Vancouver. And hopefully by that time, we'll have a lot more mass timber buildings. This means in order to meet this living demand, we need to have certain stock of buildings, mass timber buildings that's standing, people can live in there, right? This also means there will be certain amount of wood that needs to be in that building. So the material flow analysis basically keep track of different age cohorts of the building because building can have different ages. So by 2050, to meet the demand, you may have a lot of, let's say 2040, 2020, 2000 buildings still there. So there's a certain amount of wood in there. But due to the demolition of the older building, you may need to build new buildings. In that case, using an MFA, you can keep track of the new, like a harvesting demand of the wood from the forestry just to meet, the total demand of the wood in the construction sector. So this is another type of analysis, right? And the other method I want to mention is called techno-economic analysis. Again, this kind of goes back to like the resolution of LCA, where you try to look at let's say a single, like a product system, a single technology, and you want to compare, for example, the economic feasibility with your new technology, your new technology with the old one. So that's where techno-economic analysis actually come into play. And then it's often used in combination with LCA so that you can at least get a broader sense of both environmental, sometimes social, and also economic impact of your emerging technology as compared to the benchmark, right? So hopefully after this, you have a clear understanding about like different industry technology methods. And again, LCA is an important one, but not the only one, right? And if we look at these four methods, they're essentially all modeling methods, right? So if you want to do the modeling work, you will need data, right? In many cases, tabulated, very clean, organized data. But in reality, data doesn't really just sitting there, right? So you need to somehow prepare data. So what we do is that we gather the information and then we transform the information into the data we can use, right? So the information ideally can be in the table format, then you just do some regular formatting. But in many cases, it can be like a PDF article describing the industrial process. Then you need to somehow translate that knowledge, the information, into a tabulated form of data that you can use for LCA, let's say, right? So that's what I will call the extended industry ecology methods come into play, right? So let's say if you're familiar with chemical engineering, right? So if you know a particular reaction and you want to kind of like model how it's going to be, a particular chemical is going to be produced in a chemical plant, then you can use the method called process simulation, right? Using certain softwares. And then let's say if you want to understand the energy consumption of a particular mass timber building, then you can gather hopefully large enough of historical data, then you can apply a machine learning model to predict under certain climate condition, what is the electricity consumption for cooling, right? These are all extended methods in addition to the, what I would call it, like the traditional industrial ecology methods. But you do need these methods to, again, transform knowledge, information into the data. So that kind of like linked to my own research program, where I would like to use these extended IE methods, industry ecology methods, to translate the knowledge of the industrial system into kind of like the data set that's ready to be used. Then I can apply industry ecology methods to understand the, let's say, the sustainability aspect of the system I'm looking at, right, at different scales, because if you recall, we have different methods looking at different scales of the problem. And then I'm particularly interested in investigating if there's any trade-off between bioeconomy, circular economy, and climate mitigation. Those three are very kind of like good hot topics. They from the face of it, they're all very good, right? So for our own society, you may find a lot of synergy between the two, but they might also be a trade-off, let's say between the bioeconomy and the circular economy. One very good example is the recyclability of the bio-based composites. In many cases, it's really hard as compared to fossil-based composites to be recycled, right? So by using the industry ecology methods, hopefully I'll be able to kind of explore different type of trade-off and synergy between those like a large area topics. So this is a visual kind of representation of the some of the key themes of my research at different scales. And just for today, for the sake of time, I'm going to show three projects. Two of them are at like the single like product system level, and another one on the lower right corner is more at the value chain level. So you look beyond the technology, the product system, but thinking about the socioeconomic policy interactions. So, okay, so let's start with the first two, the emerging technology, I will call them. And if you think about emerging technology, right? So when we talk about the technology that's emerging, then usually we're talking about its TRL, which is the technology readiness level, which is quite low. In this case, a lot of our colleagues actually developing many amazing technologies in the lab. But if you look at a scale, TRL of these technologies are usually at TRL 4, and for the commercial technologies, usually have to reach TRL 9 in order to really fully commercialize the technology, right? So in that case, there's a gap. Basically, if you want to estimate how good, or if there's any potential like a negative impact of your technology, you need to go beyond TRL 4, beyond the lab scale investigation, right? So how can we do this? So in many cases, well, I think for a lot of us, the first thing in our mind is that let's build a model, right? So then I think, again, take a step back, think about why do we need to build a model in this case, right? So you don't just go blind and just try to build a model, right? I think the first reason why we need to build a model in this particular case is a lot of things we cannot actually measure, right? So you can measure some of the parameters in your lab, but in thinking about going to a more mature technology level, for example, how you can optimize the configuration of different unit operations in a chemical plant is actually very complicated. You cannot just measure it in your lab, right? So that's why you need a model to do the estimation. So measurement and estimation, they're two different things, right? And then even if in some cases you can measure what you want, it can be really costly. It may take a longer time. It require very sophisticated machine. It take a lot of labor, and the cost of probably renting the machine is going to be very expensive. So in that case, you probably want to actually go to the option of estimation using models, right? And another important benefit of creating a model, in my opinion, is that even if you can measure everything, right? So sometimes if you want to do like a large amount of experimentation and then measure the results, it's still going to be really costly. So in that case, if you have a model that you can easily turn different knobs, and then you can add more knobs to investigate different scenarios, that's actually going to be very beneficial. So that's kind of like fundamental drivers in many cases why we use model to achieve the purpose we want. So the next two projects are particularly focused on chemical manufacturing, right? So this is a very nice figure put together by my collaborator. Basically, he explored different ways of you can actually get the chemical manufacturing data you want. Of course, the first one, get plant data, is what we call measurement, right? But it doesn't really apply when you have like a lab scale technology. So you need to go to other techniques. So the first project is actually looking at a really theoretical, fundamental way of getting, let's say, the energy or material consumption data for making chemical, which is based on the chemical reaction itself, right? So this is a publication we published last year with my colleague. And then the topic is really to do a life cycle assessment, looking at how you can isolate lignin-containing cellulose nanocrystals, LCNCs, using deep eutectic solvents, right? And this is the lab configuration of the technology, right? So you have thermomechanical pulp that basically get merged in the DES, the chemicals, and then you leave it there at the mild condition, the temperature, and for like 3 or 6 hours for hydrolysis. And after that, you apply dialysis to get rid of the chemicals, and then do a high-speed blending to just cut those fibers into small pieces. Then do the centrifugation to get the product, which is the LCNC, right? So that's what I would call a physical system, right? Then if you think about modeling, it's all about abstracting the physical system into a mathematical model, right? So that you can actually evaluate some of the interesting aspects you want to look at. So in our case, the abstraction process is relatively straightforward, right? So we still have this vertical representation of each steps. Then what we would not be able to measure from the lab, in many cases, is the actual energy, material, and waste generation. Because as you probably know, in a lab, the priority in many cases is just make sure this thing works, right? So then you probably will have extended operation time, and you have a very not very well isolated reactor in this case. So we need to find a way to estimate the energy, material, and all the other flows, right? And also another thing that's missing from the lab scale operation is the recycling of the DES chemicals, which in a lab, in many cases, it's fine, right? So you want to make sure the reaction works, but in reality, commercial production scale, you have to recycle your DES chemical for both regulation purpose, right? Like environmental protection, waste, so you cannot just release those waste, and also from the cost perspective. So how do we estimate this type of data from the physical system is the challenge we're facing, basically. So once we get the data, it's relatively simple. You just map the flow of the information, electricity, steam, right, to the existing LCA database. So there are existing models for the BC, the electricity generation in BC. So that's the easier part. The hard part is actually to get the data that you can actually match to the database, right? So this is a screenshot of the software called OpenLCA. So as you can see, those really all different sorts of inputs for the process we get from the lab experiment and our own estimation. And I want to kind of defer your attention to these 3 lines here. So those are the 3 DES chemicals we use in the lab. But as you can see here, none of them actually exist in the existing LCA database. So that's where the modeling work gets really challenged, right? So that's where we will, ideally be able to model those individual chemicals ourselves, right? So this requires, again, a lot of data collection and transformation into the model we can use. Then in this case, because of the lack of information about how the commercial production of those chemicals are from the literature, so we kind of go to the last resort, which is using the stoichiometry of the reaction in this case. So you can pull this up and look at, for example, the standard enthalpy of formation for those chemicals, and then you can estimate, in theory, what is the energy input needed for making those DES chemicals, right? So that's kind of bridge the data gap for our model in this case. And then this is the result for the LC study. As you can see, probably most of us are familiar with the global warming potential, right? So, and then this type of figure basically shows the contribution of different major players in the entire life cycle. And again, I want to draw your attention to these 3 areas in this case. So all of them are actually pointing to the DES chemical manufacturing. This means if you think about this, the motivation of this particular technology is to reduce the reaction conditions, a relatively lower temperature, right? So in this case, naturally you will have less environmental impact in terms of the manufacturing process itself, energy consumption, waste generation. But those are what we will call embodied impact from the chemical production, which becomes more evident. So this actually leads to the future kind of recommendation for this particular technology is that there are multiple choices of DES chemicals. Some of them have higher embodied impact, the others are not. So one suggestion, of course, is try to see if you can replace some of the high impact DES chemicals with ones that has lower impact and of course still have the similar performance. And the other one is that if you can reduce the total DES consumption in the first place, of course, that's going to help the technology become more sustainable as well. So this is the first project. The second project I want to talk about still, it's related to chemical manufacturing. Right? In this case, we use another technique called process simulation, and you'll see why later. So this is another paper published. Basically, we look at producing lactic acid using electrocatalysis process and using the byproduct glycerol from the biodiesel production. So if you look at lactic acid production, which is the precursor to polylactic acid, which is kind of like the biodegradable plastic under certain conditions, right? So it's kind of a very important chemical in this case. And then commercially, the technology is to to the fermentation of glucose from starch. So that's a benchmark. And we are trying to see if we can use electrocatalysis, basically oxidation process on the glycerol and achieve the same purpose in this case, right? And if we can actually save on, let's say, energy and environmental impact. So this is a very simple illustration of this, what we call the system boundary. So we start with the crude glycerol we get from biodiesel production, right? So and then you put chemicals like electrolytes for the electrochemical reaction. Of course, you have some process energy consumption and generate some waste. And then after the reaction, you purify the product, which is a really complex process to do in the lab. And then we have two products, valuable products. One is lactic acid that we want, and we have some co-products, glycolic acid, which also have some economic value. So that is a really simple illustration of the process. And then in terms of method, actually, it's similar to the first project, right? We start with the experiment, work with my electrochemist friend, getting the experimental data, and then we translate that type of data using process simulation, in this case, Aspen Plus in particular, and we try to line up the reactors, like the purification, separation processes in this flow diagram, because as you will see later, we have 5 products out of the electrochemical process. We're only interested in 2 of them. So separate them, take a lot of steps. And if you want to do the theoretical calculation for separations, it's really, really complicated. So that's why we actually resort to this kind of like a user-friendly like a software in that case, and we'll try to use some of the internal algorithms to do the mass balance like the convergence of mass and energy balance in that case, right? And then and the purpose of doing process simulation again is to translate the knowledge of the reaction itself and the possible energy consumption into the quantitative information, such as electricity use and steam consumption that we can use for the LCA calculation. So as you can probably think about this is a relatively complex process, and we want to compare different scenarios. So what we did is that instead of using OpenLCA, which is a really nice software, has a very nice user interface, we rely on this Python package that basically you can program your own LCA model. In that case, give you more flexibility, right? So if we dig a little bit deeper into this case, we can see here, this is probably a very typical data sheet you will get from your daily lab experiment, right? So we have, for example, 5 different products that's being produced. And then we have, for example, the reactants, like the electrolytes that we need for the reaction. And then we have different operational conditions, right? These are the information very typical from a lab technology development, I guess. And then we translate this into a process flow diagram. In this case, for example, we have the reactor here, right? So we do like a batch reactor in this case. Then we generate a mixture of products. Then we put another reaction called methylation. So you convert basically those acids into esters. And by converting them into esters, they're relatively easy to be separated during distillation process. Then once you separate them, you get the 2 esters you're interested in. One is one is actually later converted into lactic acid using hydrolysis, and the other one is the glycolic acid, right? So this is a process that we actually simulated in the software, which gives us the material, waste, electricity, steam consumption for the process, which then be used as the input to the LCA model. And we can actually play with these variables and see if we change some of the conditions, what is the environmental impact of this particular technology, right? So this is overarching structure of the model here. So we start with some again, some technical knowledge about the process. Then in this case, we put that into the process simulation, then we get the data, right? So we start with the information knowledge, then we get the data. So we have the data go to the LCA calculation and also go to the TEA, techno-economic analysis. And so my Python code has two major modules. One is for the LCA calculation. The other one is for example, the net present value and all these technical economic metrics. And then for each of the module, there's a capacity to do some uncertainty analysis, right? So if you think about your input of electricity or steam, you may actually have certain distribution as compared to just like a single data point. So you want to build in this kind of flexibility in your model. So in the future, if you have more data, you'll be able to see how uncertainty your model result is with respect to the uncertainty in the input data, right? So then once you generate, let's say, the distribution of net present value and global warming potential, one is for economic, the other one is for climate change, you can do what's called a global sensitivity analysis, which decompose variation of your results into each of the input variables. So you will know which input variable, for example, let's say, the electricity of consumption of the electrocatalysis process, or for example, the consumption of electrolytes. So which parameter actually has more impact on the uncertainty of the result, right? So this is like a one pass for one technology. Then with this model, we can just change the input, then we can do it for the benchmark product or any product that we're interested in, right? So we can have multiple products in this case, and then we can compare them, basically compare this catalysis processes compared to the fermentation process. What is there any benefit, right? So, and then of course we actually then open access our code and data on GitHub, so everybody actually can look at it. So I think the key finding, the message from this particular project is that in terms of chemical manufacturing, if we couple electrocatalysis process with low carbon grid electricity, this is really going to be a game changer for many of the chemical production processes. So this is a simple illustration, the waterfall chart, right? So we have the default scenario where we have fermentation of glucose for lactic acid production, and also we put in some of the fuel aspects. In this case, we have, let's say, gasoline, right? So this is more like a current status of energy and fuel production. And then if we start to kick in the electrocatalysis process for lactic acid production only, we can see about 40% reduction in global warming potential just for producing the same amount of lactic acid. And then if we start to think about fuel production, right? So if we use, for example, pyrolysis of the woody biomass, and then we do electrocatalytic hydrogenation to produce biofuel as compared to producing gasoline, then we can further reduce the greenhouse gas emission out of the whole system. So in this case, we're talking about two products in the same system, right? So so I think just a quick summary. If you think about these two projects, they're both looking at the product systems, and then they're both actually helping to estimate the potential impact of a relatively early stage of technology, and how we can actually further make it better, right? So it's actually help to kind of like focus the research for early technology design. And we also find, interestingly, material actually plays a really important role in both cases. In the first case, we talk about DES chemicals. Those actually have a lot of like a high embodied carbon impact, right? And in second case, we have sodium hydroxide as an electrolyte for the electrochemical reaction. And we basically play with a different lifetime of the electrolyte because eventually you have to replace it, right? So then we find it actually has a really large impact on the uncertainty of the result, just again, because of the embodied carbon in those chemical production. So, and out of these two projects, and of course, along with the other projects we've done, we also identify some challenges for modeling, for using LCA for modeling the environmental impact of bioproducts, biotechnologies. And the first one we see is that there are just so many chemicals, just chemical alone, there's so many chemicals, so many like a potential application of bio-based precursors to make chemicals, right? So that we can actually decarbonize our chemical industry. So how do we prioritize the effort, right? And second one is that we find there's a really large data gap if you recall the first project, we don't find anything about the DES chemicals. So this kind of data gap is really important for the future research. It's really a big challenge for applying LCA. Actually, not just to bioeconomy, but for any of the system analysis. So that actually leads to my the PhD project, like the project of my first PhD, basically trying to look at these two challenges. So I think many of you probably have seen this from the US Department of Energy, right? So this is a figure from a report. Basically, they list the high value added chemicals for different applications. The applications are on the right-hand side. And I think for a lot of efforts we're doing here, for example, in our own faculty at BPI is trying to find those more like a building block of precursor chemicals that we can make for our renewable resources to replace the fossil-based precursors. So we can still have those high-value chemicals we can enjoy, but we start with something that's really sustainable, right? But as you can see here, in those how it's modeled in those databases. And we're trying to look for is that for these individual LCE models, right? So what are the fossil-based feedstock going into making those high-value chemicals? And what are the bio-based alternatives we can apply in this case, right? So we kind of try to map out the potential. So in this case, then we start to extract those LCA models. And then once we get these models, we then want to actually play with the ways we can actually modify. For example, we swap the fossil-based precursor with the bio-based precursor we're interested in. We can change the amount. Right? In some cases, we actually, when you use bio-based products, you can reduce the amount you use. But in other cases, you probably have to use more. Right? These are the modifications we want to do. And as probably you can imagine, with all these chemicals, all these different processes, if you do that manually, it's going to be really time-consuming. So that's why, again, we rely on this fundamental package, and then we write our own tools, which is a recursion-based algorithm. So you basically dig into layers of LCE model, and then you try to, let's say, swap the fossil-based feedstock with the bio-based feedstock, right? Once this tool is applied, then we have basically different LCE models, as many as one, right? Then we can run the LCE analysis and then compare, in this case, right? Compare the benchmark and the one we modified, and hopefully, in the end, we can show people. The goal is to create, let's say, a dashboard, right? So people can have a drop-down list saying, okay, this is a high-value chemical, and if I want to replace the fossil-based precursor with this particular bio-based precursor, what is the potential to reduce climate change impact, right? And also, the fundamental data we can contribute to the community is also quite phenomenal, I think. Right, so that's what my PhD student is trying to do, and I think she's going to be successful in this. So if you, again, think about the contribution, the relevance to the bioeconomy. That's our topic today, right? So we really hope to help to prioritize the effort of the limited resource we can use to kind of like really look for bio-based precursors that can have a maximum or large decarbonization potential in terms of, at least for the chemical industry. And also by doing this, we'll naturally identify some gaps, data gap, model gap, right? So in many cases, you don't have the model to represent the chemical production. This actually leads to the second project, right? So again, if you think about modeling, right? So I guess many of us actually have seen this figure during the past 2 years, right? So if you think about this, a horse can be a real physical system, right? So, and then drawing a horse on the paper is actually translating the physical system in in this case, more like a artistic model. But yeah, you can think about this as like a modeling process, right? And in order to do this, if you get a really detailed representative touch, let's say on the tail, then basically you can have a really representative representation of the physical system, right? And then if you start to lose this kind of detail, and in some cases you have to kind of resort to other similar animals, then in this case, using proxies of other animals back, then you probably will, it's still okay, but you can see it's kind of deviated quite a lot from the reality. Then further on, if you have no idea of how to draw this lag, or in this case, you have no idea of the product system, they may have to make very oversimplify the assumptions, so that you still have a horse, but the problem is not real in any case, right? So this actually represents kind of a challenge of the data gap in LCA community in general. So this is a general description of how we actually do the modeling in LCA. So let me actually speed up here a little bit. So if you look at here, let me just enlarge it here. So you start again with your technology, right? So you have the technology description, and then you look into a database and you try to see if there is any exact match of the technology, like electricity you want to use. If that's the case, it's relatively simple. For example, if you find an industrial process that actually describing how to make sodium hydroxide in this case, then what you probably want to do is just change the electricity provider. If your sodium hydroxide is produced in BC as compared to in Germany, probably just want to change the electricity grid. That's probably the largest contributor to this. So it's relatively simple. Then in many cases, you don't find an exact match in the database, then we will have to go to the proxy selection in this case, right? So is there anything similar from the same industry? Or in other case, I just probably have to use a precursor chemical in this case as a proxy, right? But in even more cases, you will find nothing. In this case, you really have to create a model yourself. And the two examples you saw before, one is using a theoretical calculation, the other one is using simulation, right? So this is kind of give you kind of like a illustration of how you will start with the knowledge of technology and try to get the data so you can do the LCA calculation. So let's see. Yeah, so I think the issues we're facing here is we want to either do, when we don't really have an exact match, we need to do either proxy selection or new data creation in this case, right? So, and then in order to address these issues, we have approaches, right? So data-driven approach, like mechanistic approach. And the difference at large is that data-driven approach in many cases is trying to set up the correlation between your input, right? So you have a process, you have different input, like energy, material, then you have the output, let's say yield of a particular reaction. So there's a correlation between the two if you have enough data, right? So you don't really need to know how these materials is converted into the like intermediate products and then converted into the final product. So that's the data-driven approach. In many cases, this correlation. Then mechanistic approach is really try to understand the causal relationship, right? You have A and B and then you form C, then you want to have a model that represents this physical relationship. And the perspective approach is slightly different because it's trying to look into the future. Because in many cases, if you want to do a model, I want to say, okay, what is the environmental impact of my technology if I'm applying it as of now as compared to applying in 2050? Even the technology is not improving, something else is going to improve. For example, electricity grid, right? It's going to probably get cleaner over the time. Then how do I know what is the 2050 electricity grid in a particular place? So that kind of data gap usually will need to be addressed by perspective methods. So here, for example, I think data-driven approach usually will involve machine learning models. I guess many of us are familiar with, right? Mechanistic model, actually the two examples I showed, the process simulation and the theoretical calculation are all based on mechanistics of the chemical reactions, right? And the third one is perspective. So learning curve is one of these. And the other one is called IAM. IAM stands for Integrated Assessment Model, which is a really large model that couples macroeconomic and like activities and climate change. So that's a lot. That's usually in many of the policy design, right? So, and then if you look at how these methods are actually addressing different issues, and most of them are actually looking at a new data generation because that's more like a larger issue. So. No, actually, I forgot to mention, this is from a review paper we submitted and hopefully get accepted soon. So we also did basically a heat map looking at all the methods we reviewed and try to categorize or characterize them based on, for example, domain knowledge needed. If you want to use this method, how hard it is, what is the learning curve, how can you automate the process, and all these information. And through this publication, we hope that we can provide guidance on how people actually can use different methods to bridge the data gap, right? So, and also specifically for sustainable bioeconomy, I think through by bridging those data gap, we'll be able to help to have like a faster, more streamlined LCA for for all these bio-based technology assessment. So okay, so I think just a very quick like a summary of how we can actually apply LCA for bioeconomy, right? So usually, if you recall, it is for single product systems. So what do we really need is usually for emerging technology, we need the lab data, sometimes extended lab data, for example, what kind of equipment you're using, the power of the equipment, and some of the understanding of the industrial processes, how people actually treat, recycle different solvents, right? And the benefit of using LCA, I think, for bioeconomy is quite straightforward. You do the benchmarking, and you will be able to do some hotspot analysis for future R&D, right? And then that's actually about the two products system level analysis. And the third one I'm going to talk about is more like a complex system of supply chain. If you think about bioeconomy system, right? So it's actually beyond the technology, beyond the product system itself. You have to cover the whole supply chain, the whole value chain in this case. This means you're not just looking at the development of the technology, which is kind of the focus of the previous two projects, but you're actually trying to see how your technology can be deployed at a larger scale, right? So this means you need to consider socioeconomic and policy interference to your system, right? So that's if you again at a very high level, if you look at the key elements of a bioeconomy, right? You have, on the very top you have different entities here, right? So you have like the natural entities and the industrial entity and the human entities that like a kind of spread across the value chain of a bioeconomy. And beneath that, you will see what? You will see many endogenous and exogenous drivers. Endogenous drivers will be, for example, your supplier. Your supplier's decision is going to affect your decision, right? So, and exogenous variables can be like the policy mandate. So these are the important factors, drivers of the bioeconomy system. And then because of those drivers, there will be feedback loops between different entities in the system. So, to kind of like analyze this very complex system, there's a established methodology called like a system dynamic modeling. So this is a paper we just got accepted this morning to do the review on the system dynamic models on bioenergy in particular. As you can see, there are a lot of like loops in there, and we find that this is a really good methodology, but there are some research gaps here. First one is we see that how people represent technological information in these models are static. But if you look at a reality, right? So in this, for example, if you have an investment in a new technology, it's likely the technology is going to be better in that case. And then in this case, you'll improve the capacity of the technology, the market share in the market, right, of the technology. Then again, that's going to very likely attract more financial support in the next round of the modeling. So this is a dynamic process. It ideally will represent how a particular technology is favored against the other one in terms of this investment improvement cycle. But this is actually not represented in the current literature. And the second one is about interference from the environmental side, right? So if we look at this again, this is an example of bioenergy. So let's say we have a policy for bioenergy promotion. This is going to lead to the basically increased investment in bioenergy, right? So, and then this is going to increase the share of the bioenergy in the grid. Naturally, can lead to the emission saving. This is going to increase the attractiveness of the bioenergy. So this is kind of like a beneficial, like reinforcing loop. But in reality, it probably is not always the case, right? So if you have more bioenergy, you may actually cause some loss of biodiversity. In this case, there may be some negative impact. So that's going to determine the attractiveness of bioenergy. And then in this case, you may have some negative feedback actually go into the loop. So this means the outcome, the environmental outcome, should be part of the driving force of the feedback loop, but which is also not represented in the current literature. So that's why for our next project, we really try to build in these two feedback loops. One is for the techno-economic, the other one is for environmental, right? So this is another PhD of mine. His project is basically try to unify this assessment in a common platform, so we can actually kind of like do the analysis more streamlined. So, so the platform was also based on system dynamic model with 3 segments, right? So the first segment where we want to look at how bioproducts are produced, and then upstream we will have, for example, forest resource management, right, and other forest companies as compared to more like a biorefinery concept. So there might be some competition for the feedstock, but in other cases there might be some like collaboration if you use a residual, right? And then also if you think about it like a new bioproducts, it's likely the distribution channel is not built. So the growth of the distribution channel will be contingent upon the customer choice, and then that's actually going to affect the product demand as well. And this will supposedly loop back to your biorefinery, the bioproducts module to determine whether the scale of your production. So as you can see, all these kind of linked dynamic loops should be represented. And then, as we mentioned, we want to understand both the environmental and the economic part. So these should be the models that are actually external to the system dynamic model, but be part of the framework, right? So we can actually look at investment and also policy in this case. So I'm going to quickly skip this slide, basically. This is one tiny bit, I promise, is about more like a recent interest. So we cover the 3 projects, and the machine learning part is actually my recent personal exploration here that's also relevant to bioeconomy. So this is a project, this is a paper we just recently published. It's predicting the litter forest generation from the forest using machine learning methods. So as my FRM colleagues probably have more knowledge than I do, is a litter forest is part of the carbon cycle, right? So it's part of like these stuff that you actually got in the forest, right? So so there are like monitoring sites in China, like multiple of them just using these traps. So they measure annually what is the quantity of litter that's generated in a particular forest, right? So we got this set of data just a little bit shy of 1,000 data points, and with different features, for example, like the location and climate data and the sum of the forest type, the categorical data, right? So if you ever work on a machine learning model, this is a pretty typical like a data pre-processing pipeline, right? You take the data, which is kind of like messy, then you do some cleaning, get rid of the columns where you have too many missing data points that you can also use for prediction. And then you, for example, you try to, if you have correlated features, you try to actually separate them or just keep one of these. And then you do some encoding because, again, categorical data, the text, the strings, basically the machine cannot understand that. So you need to encode that and then kind of like separate the train and test data set. So then start to train different models. So we explore different like major machine learning algorithms, right? Some of you are probably familiar with random forest, right? So and then there are like boosting algorithms as well. So both are like tree-based algorithms. And we actually settled what's called a MIRF, mixed effect random forest, which is good for looking at like a subclusters of data and their relationship with the target variables. So if you look at the contribution, so if you look at the entire data set, we actually have a quite also incremental improvement as compared to the benchmark, 0.1, right? Depending on which domain you are. If you're looking, let's say if you're in a natural language processing or computer vision, 0.1 increase is massive. But for our case, probably it's not that much. So then I think the more substantial contribution is that if we start to cluster those sites into different regions, then we see a substantial improvement in the prediction. And this has physical meaning, because if you want to understand, let's say you want to predict the litter forest generation, you probably don't know exactly which site you're looking for, but you probably know which region your forest is. So that's going to actually help give you basically a different level of like flexibility to the prediction. And of course, then we actually try to understand the importance of different features and their relationship in this case, right? So, okay, I think I'm kind of quickly wrap up with my presentation here. This ongoing project with my colleague here is trying to look at how we can use machine learning to help make this like a cellulose form in better in terms of a better performance, right? So you have different technologies in here, and we start to collect data in this case. So we have, let's say, the performance metrics here. That's our targets for prediction, and then we have different numerical features. For example, I think drying time and all these things, and then you have categorical features, the different drying methods and all these. And then you also will find some correlated features, which is actually not very good for regression, right? So what we did is we decorrelate the material and concentration into put them into one vector, and then we can actually concatenate that with the other vectors. So in this case, we can have the input layer where we have all these vectors with encoded numbers and put that through artificial neural network, and then get one output, which can be the porosity of form, basically. So that's an ongoing project, and we're trying to, again, the challenge is actually to collect the data in this case. All right, so and I think this this kind of research in general is going to help bioeconomy in terms of reducing the resource, the time you're going to spend on making a material better. Right? So you kind of get a narrower range to do trial and error, and also helps to collect inventory data because they have a smaller range to look at in terms of like the operation condition, material, and all these things. So a very quick summary of all the topics and like the methods I've explored in the previously and currently. And I hope the key takeaways from my presentation is that first of all, I think next time if you think about sustainable bioeconomy, you should have like a systems mind, right? So it's not just about technology, but really need to think about other aspects. And there might be like the trade-off and the synergies we need to look at. And if we think about the question, right? So how can we use industry ecology methods to help make bioeconomy more sustainable? Right? We see a few examples. If we look at individual product systems, we can use LCA, right, to help to guide the future technology development. And then if we look at a more broad, complex value chain scenario, then we need to account for example, the human behavior, the socioeconomic impacts. And lastly, we explore some of the machine learning applications, which can actually help to inform R&D as well. So lastly, I want to mention that without the hard work of my brilliant students, I won't be able to get here. So really kudos to them. And this is my last slide. So if you're happy to answer any questions you have, and sorry for going over time, big time, sorry.
Work and thank you so much challenging from what we can produce in terms of bioproducts to what will really make a difference and all those complications in between.
Which projects is that? I can try to use this actually. 70 what? Sorry. Oh, 72. Okay, that's easier. Yep. Oh yeah. So this is a technology, right? So and then what we really want to look at is actually if you let me enlarge this a little bit. So we want to look at different like performance metrics, for example, the porosity of your product and all the other metrics that I'm honestly not very familiar with. So yeah, that's the goal. That's the target. We want to predict this type of performance, given the input data of the methods for driving, for drying, and the chemicals you use, the time, and all these type of information. So you can see here there's a temperature, surfactants used, and like there's a correlated resin material and concentration. Yeah. Yep. Correct. Yeah, that's actually a very good question. That's actually somewhat related to the correlated feature, the first and second column, right? So like let's say the concentration of the materials is kind of dependent upon what material you're going to use, right? So in this way, we try to kind of, instead of like two-dimension column of vectors, we try to make it like one, like basically a 1D, one column vector in that case. Yeah. Sure. Yeah. Thank you for the question.
Okay, we have a couple of questions
online.
Hamish Vanderven asked if there are any examples where proxy selection has led to results that are, in hindsight, completely inaccurate.
Oh yeah, thanks for the question, Hamish. Yes, I think that's, in many cases, it is. So I don't really have an exact example off the top of my head, but if you think about proxy selection, in many cases, let's say one example is that instead of having a specific chemical you use for a reaction, in many cases, you can only pick a general inorganic chemical production process. So in the database, there are like a specific chemical production, but there is a general process called inorganic chemical production. So in many cases, if the individual chemical production is definitely not a choice, then you have to kind of resort to that very general inorganic production process, which is the average of all the other inorganic chemistry. So in that case, it may very likely lead to a very not accurate answer. Then in that case, you have to apply uncertainty analysis on top of your choice. Yeah.
Thanks for that, Qingshi.
Thanks.
Question about how often the information to build the model is affected by intellectual property, and that information must exist, but you can't access it. And I noticed you're very interested in making this work open.
Yeah, thank you, Sally. Yes, this is actually one of the big issues. And according like my personal experiences, because I was a consultant for a few months. So in that case, I do really see the relatively openness from the industry. They are willing to provide you the data because they want the report done, but they also have to sign NDA, right? So in this case, we can kind of like have aggregate data set without like individual ingredients of the product, but that's the best that we can do. And I think that's even a better case as compared to doing the research. In many cases, research, if you don't really have direct kind of like a relationship with the startup company or the manufacturer, you don't really have any idea about like the exact electricity consumption on that. So you really have to, again, go to using some proxy processes, or really have to make some really theoretical calculation. Yeah, in terms of, for example, heat of evaporation, this kind of thing for the evaporation process.
So I think I also, sorry.
Yeah.
I wanted to let people know online and in the room that next Thursday at noon, we are having a Faculty of Forestry panel discussion, moderated panel on old growth and the path forward in BC. We have excellent people on that panel, including Gary Merkel, the author of the Old Growth Strategic Review, Rachel Holt, and Cam Brown, who have produced different analyses of the amount of old growth left, and Chief Robert Dennis, who has made recent arrangements on old growth protection in collaboration with Western Forest Products. So please join us for that, again, noon next week. That will be entirely online. And in 2 weeks, we'll have Danielle Nace for our last research seminar of the term. Thank you.
Thank you. And thank you for those who are attending online. Thanks.